So you can hear me? Is it on? Yeah. Hi, as you said, my name is Mikael. This is my Twitter handle right there. And today we'll be talking about how to apply basic functional programming to and apply to UIs. We'll talk a bit about a simple form of unidirectional data flow and how we could make our views simpler. So, kind of touching upon what Andre was talking about earlier, but just focused on the particular views. So, the goal for this talk is to try to make us, to get us to reflect about how we build our front-end systems. Maybe give some inspiration to how we can make it simpler instead of complexity. So by thinking of our entire application as a function of state and abstracting the input and output to the far edges of our system, we can create a predictable and easy to maintain application. So along the way for this, we'll examine how we can use the most basic building blocks we have, functions, and how we can use composability for building more functional style views and compose different functions to more smarter functions. So first, so how did we get to this stage? How do we really need to think about how we make UIs, how we make view programming? Is it necessary to reevaluate this? So in the beginning, we had the traditional server-client relationship. It was an easy request, response, render. That was it. So simple flow, what was rendered on the client was our system output. If we did an update, even if it's just a tiny bit of update on our page, we had to do a complete refresh. So it had its drawbacks, obviously, but at least we had the complete static models of our page. So moving on, the web matured. We found we had a need to do more dynamic updates. We wouldn't want to have just changing a text in one paragraph on our page and do an entire new page reload with a new HTTP request, a new response, a new render. So we wanted a more dynamic way of doing views. So we started moving more code from the server to the client. So instead of sending all our entire structure and our entire content on initial load, we do now AJAX requests and dynamically create our content on the client side in many cases. So what happens actually is we build up a massive time-dependent state and a representation of the DOM, and we no longer have these complete static models as we have with just plain old HTML. So we can think of our pages and applications like multiple pieces of individual code, which in some way are connected and need to communicate with each other. So the problem is we often have our applications and we don't have a clear direction of how these messages go. So our pieces of code can send messages in multiple directions, and further, our pieces can be tightly coupled. So in many cases, it's impossible to just look at one piece of code and imagine what the output will be. What if two pieces share some sort of data and one of the pieces changes that data? What happens to the other one? So this is a model that needs to be simplified. We need to be able to reason about our system in a much clearer way. So we have solved many of these problems already, just not in a UI context, and we can use a more functional style approach to our systems. Functional programming can allow us to think about our code in simpler ways, just having two connection points to our components or to our pieces of code. Its input and its output. So instead of having the multi-directional different communications by our pieces, this will cause a tree. So, or even if our system gets large enough, you can see them as multiple trees connected yet again by trees. So you can think about a tree of trees, if you like. So this looks familiar, though, to our old ways of thinking about content. Just like the HTML pages we had, we can read this code from top to bottom and statically in our head mentally reason about what the output will be. So to achieve this kind of things, our pieces need to show some certain traits. One trait we'll talk about is referential transparency and purity. So let's just talk about function for a moment. Andre touched upon this as well, but in its most basic form, it's just the ability to group a set of expressions which can be reused in different time and place in our system. In other words, a function is a set of operations which take some information, transform it, and gives another piece of information as output. So referentially transparent functions are a subset of, of functions. They have a specific trait that in simple words, a function is referentially transparent if at invocation level we can swap out the function call with the result of the invocation. So let's take it for instance to see that this isn't as advanced as I made it to sound. We can have a square function which if you pass the number 2, it results the number 4. So we can swap out just our invocation with the number 4 and our system would still behave in the exact same way. Expressions such as this one can also be referentially transparent. So in JavaScript, we have built-in operations like add, and that is by nature referentially transparent. We're just adding 2 numbers together. You don't do any other effects on the system by just adding those 2 numbers together. So we can think of a simple plus or addition as the result of its addition because the operation itself is referentially transparent. So replacing our expression with the result, it wouldn't change and alter the behavior of the system at all. In code, this would look much like you'd expect it to. So we can have a function square returning the number multiplied by itself. And we can think of 2 invocations adding together as just 2 times 1 invocation, or we can think of it as 2 times the result of 1 invocation, or just a resulting object, which is, even though it's just a scalar value. This causes, of course, predictability, because they're deterministic, right? So no matter when or where we invoke our functions, the output will be the exact same thing, given that the input is the same. So that's testability as well. Our function and building blocks are predictable, they are testable. Just as we can replace expressions of adding 2 numbers together with the result, we can also simplify series of function invocations, or series of function calls, if you will. So multiple function calls can be thought of as 1 function call, or just the last call in our message queue or message call stack. So we can group a series of functions in any way or permutation we want. And this helps for thinking about our large tree that we had from before. So instead of thinking about it as a very grainy tree, we can mentally skip all the details and think of our tree as a much more simplified tree. So again, this requires our functions to follow the same pattern. They need to be referentially transparent. So with referential transparency, we also can have composability. So we can derive new functions that are also referentially transparent. We can take 2 functions with the same argument list and the same return type, and we can compose them into a new derived function. Composing can sometimes be denoted as a dot, but in JavaScript, of course, it's just a function. So a function taking 1 or more functions and returning a function yet again. So this is called a higher order function. Composability of functions can allow us to build larger systems, larger applications, just by adding multiple or small pieces together. And each of those individual pieces are easy to understand and simple to understand. So what this buys us is the potentiality to look at one single piece, and without even knowing the rest of the system, just by knowing its input, you can see what it should output. Another way to use composability is to attach a predefined set of arguments to a function. So this is called partial application. You probably heard about this. We can derive a new function which takes any number of arguments, arbitrary number of arguments, fewer than the original function. So we gradually build up our application one function or one composing at a time. So by having simple building blocks, we can build our application one step at a time. One important feature for functions that is referential transparent is purity. So we can't have side effects between functions. Not one code inside one function can alter the behavior of a different function or a different section in your application, except for what it outputs. And often we can have these kind of side effects without even knowing it in our applications. So everyone probably knows this. JavaScript objects are per default mutable. So this means that two functions, if two functions get passed the same object, and that object is changed in some way inside one of the functions, the other function has to live with the consequences of that change. So this is a fairly common side effect, and often it's fairly common to have these sort of bugs in larger systems. You can pass in options object to two sets of plugins or two sets of code, and one of them changes the object, and the other one then has to live with the consequences. And so this doesn't only apply to objects, in a sense, it's all values passed by reference. So this is one way our functions can be tightly coupled between them. There might be a better way to avoid the shared mutable state of objects leaking through our system. Instead of passing mutable objects to our functions, to our building blocks, we can use immutable objects. Immutable objects works in a fairly the same way as other objects, but instead of altering the existing object, you would create a new object when it's changed, and you would have to store a reference to a new object. This means the original object is unchanged, and we can still have a reference to it. Not only will we avoid accidental shared state, but we will also be able to use and reuse our old structures in different ways. As we always create new references or new objects when we change or swap any of the value of immutable data structure, we can easily check if two objects are the same. There's no need to have deep value checks, or the only thing we have to do is check if two references point to the same memory slot. If they are, their objects are equal. So this is a very cheap operation. Reference checks aren't costly at all. In contrast to deep value checks, which can be very costly, especially with large structures and large trees. It might sound like immutable structures are not very memory efficient, but that's in most cases not true. So we can use something called persistent data structure, in which if we change a small bit of data in our larger structure, we only swap out the new data in the particular tree, and we share the old data between them. By having immutable values this way, we can pass the same object to different functions and not worry about having accidental shared state, not worry about if the object has changed or not. So the only part we're concerned about is what the function outputs. This is a simple contract. Everything we see can be applied to components as well. So what is a component? Most of you have probably seen React. React or any other virtual DOM or library or framework or what have you can allow us to write, not particularly, you won't write HTML templates, but you will write HTML representations, either using JSX or just plain old JavaScript functions. And these libraries have smart ways of updating your DOM. What they do is they build up an internal abstract tree of abstract DOM tree, And only when the internal representation has changed, the appropriate update steps get taken to output the actual DOM. The HTML representations are often called components. A component is thus a small piece of view code, just like HTML elements, and contain one or more elements themselves, but it's in code. So by having our components as a part of our programming language, we move views into a more powerful environment instead of moving JavaScript into a less powerful one. HTML elements are very restrictive by nature. They can only communicate with themselves and with each other by using text or numbers as attributes. This is not the case with components. Components are much more powerful and can communicate much clearer with advanced structures. We can pass objects. And as we know, the way JavaScript works, when you can pass objects, you also can pass lists, you can pass functions, and you can even pass something like observables. Components can have the same traits as regular function. They can be referentially transparent, and they can be composable. So the same way we can derive a new function, we can also derive a new component. For instance, we can compose two components, creating a new component, which is the combination of the two. We can call them higher order components. So we can also partially apply components using higher order components. By partially applying some bit of information to a component, we can create a component that is much more semantically clear and is much more focused on what its goal is. Components can work exactly like functions. Stateless pieces of code which transform one information, one input, and result to another information as an output. Of course, we can use other functional patterns and functional building tools for our components as well. We can use map, we can use filter, we can use reduce, or even decorators. So by applying different functional patterns, we can take very simple components, deriving components with more functionality just by adding small pieces together. So a huge advantage of this is that we're still able to use our components in different ways, in different settings, in different time, or individual components and the new derived functions. We can output our components to the DOM by using a function that takes a component and a mounting point. This can be achieved by using something like React, Virtual DOM, any Virtual DOM implementation, really. So this would diff the output we had with the actual DOM and just perform the operations needed with the DOM, right? But the important part here is we update the DOM to reflect our truth in the code, not the DOM being the source of the truth itself. And of course, our system is referentially transparent, is pure, so we can have a predictable output and testable output. We can do rendering multiple times with the same input, and the system wouldn't actually do any DOM operations. It might seem like we have a problem here, though. It seems like we continuously communicate with a rather huge side effect, the DOM. This will break our system being pure and referentially transparent. But even if we have immutability and we take care of having all our functions pure, all our components pure, and referentially transparent, we still have to integrate with the DOM. We still have to have some output for our system. The DOM is just a massive blob of states and a huge mutative side effect, allowing our functions to be tightly coupled. So just as we saw with accidental shared state between objects, we can have accidental shared state and tightly coupled through the DOM. If all our building blocks can communicate directly with the DOM, directly to the integration point that is the DOM, our functions aren't pure, they aren't referentially transparent, even if they may look that way initially. So there's no avoiding the integration points, but we can move all the integration points, all the stateful communication to the far edges of our system, to the far edges of a data flow graph. we don't have to worry about the state leaking through our applications. We can have one top global immutable structure which holds all of our information. We can pass the global structure as input to our top component, and that component can distribute its state as input to the different objects. This is also true for integrating with the DOM. Remember, DOM is just the integration point. It's just our output. By having the data fetching integration at the beginning and let the data flow through our system to its end output to the DOM, this can simplify how we can think about system. And by directing all the communication from top to bottom or start to end, we get what is often called a unidirectional data flow. So remember again, we have referential transparent components. We can think of our application as a single function call. Mentally, we can replace the entire tree with just a top function call and think of it just as a function of state. So sometimes we have to do updates. We have to swap out some part of our application states. After all, applications that just render some output are rather dull. So what we do is we send a message back to the top state or from any other place to the DOM, to the top global structure. And when a value of the immutable tree has been swapped, a new invocation of our system occurs. So this is, think about it, it's essentially just the same as doing a complete browser reload. Just, we can go back to our simple mental model that we have with good old HTML. We can read the page from top to bottom without having a massive blob of mutative state buildup, but by having distinct states over time stored at the top, abstracted to the far edges. So none of our stateful interaction is leaking through our system. By sending messages to our global state, we can get some sort of revision history between our changes. Every time something in our system changes, we get a new iteration of the top structure. This means we can step through our system and react to an error if some uncaught error occurs. So then we can pop the last state and go back to the working version. We can even build test tools, and instead of having to click through our applications, we're using some tedious tools like Selenium to click through and record a session. We can just take our history, serialize it, and step through it through time and check our output for each iteration. This is much simpler to build robust systems. So another use would be to do something like serialization of our top application state if an error occurs. So by serializing the entire application state, we can log it to a logging server, and on our local development machine, we can take the entire state and the same code base, the same revision, and reproduce any error that occurred. This makes it really easy to fix some bugs. Initially, this render loop we have by sending data down and updating and doing a new loop, or a cycle, if you will. Initially, this render loop can seem like it would be slow, but in most cases, it actually works rather well. As we follow, of course, the principle of referential transparency, we know that if the input hasn't changed, the output shouldn't change either. This means we can omit updating a component that's past input that's unchanged from the last iteration of our application state. So this will only update a leaf node or any of its parents that it has changed. None of the siblings or rest of the trees, rest of the components in the trees should update. This works really great with using something like React or any other virtual DOM implementation, which is where is diffs the output as well, so we have double diffs. There's of course no silver bullet as any library or implementation is. So if you do high frequent updates, you might stress the garbage collector, you might do more memory and CPU time. But for the most cases, this works pretty good. So to summarize, we've seen how we can use patterns from functional programming to program our views. And this is often thought of as a poor fit due to the stateful nature of UI programming. The DOM is just a side effect, right? So we can see by thinking our system as a function of state, where we have the global structure at the top and global immutable structure to avoid shared mutable states, and using a render loop to achieve a static mental model, much like we had with the good old HTML. But this, instead of having static HTML, we have still the power and the flexibility of programming. So it's merging the two worlds. All of these ideas can be realized using React or using any virtual DOM implementation. It's just an idea, it's just an inspiration, it's just a way you build your applications by using, thinking thoroughly through how you build your functions. And my hope is, and it seems that it might be heading that way, is for React to get built-in support for stateless functions. As for now, it's not that straightforward. You have to use something that looks like classes. So this is why we created a very, very small syntactic sugar on top of React and a smart logic to check whether or not the components should update based on the past input as immutable structures. And this library encourages these kinds of patterns we're seeing. So if this talk was at all interesting to you, check out the Omniscient project and help on improving on its ideas, or just check out the reading material, or say why you disagree, or if you even disagree. If you're interested in learning more, these are some links you can check out. I didn't get much into how immutable data structure works, just briefly hand-waved over it, but you should check out Lee Byron's talk from JSConf, which goes much more into it and has great information. You should also check out ClojureScript library ARM, a library which Omniscient has built most of its core ideas from. So, thank you.
So, again, we're on the sofa time and honest questions. Are there any questions? There's one right here, and there's one over there.
All right, very good stuff. So with the global big state approach, the benefits are obvious, like global undo and state serialization, and etc. And that is assuming that all the UI components are built with this specific framework, whether it's Omniscient or React. And okay, so let's imagine that in the next 2 years, web components are the next big thing. So if we're using extensively web components, they own their own state. So then your global big state will not have everything, and you will not get the benefits that we mentioned. So what to do?
My argument is that the next big thing isn't really web components, and probably it is not going to be. But you can have like windows to your applications and using this style of architecture, and other parts of your system doesn't entirely follow that. You can have subparts of your system using it. You're not restricted to using one type of architecture, one type of paradigm in your system, but you use the paradigms to fit the type of problem you have. So I don't know if that answers your question.
There was another question, second row to your right.
Thank you. Thank you for the talk. I was asking myself, do you believe that the fact that we have the HTML tags inside the JavaScript, like with JSX, is necessary? Or can we move to something like Reactive.js, where the templates are externalized?
Yeah, so your question is how I feel about JSX. Is that pretty much it?
Or do you feel it's necessary for this approach?
No, it's not. JSX isn't necessary, and often I don't use it at all. You can just have functions, and that's what JSX really is. It's just a small transpile layer to a function call, which is a kind of a hairy syntax, but you can make the syntax clear, just like in Cycle. It's clearer, or it's easier to use. But you need to have an internal representation of the DOM and the ability to do smart logic for updating to be able to have efficient render loops. So some sort of representation of HTML in code is required. But I think that's the direction that you might be headed, to include the output to the more powerful environment that is programming, instead of moving programming into the views.
All right. Thank you.
Oh, I can see a hand over here and over there. Who's going to be first? Oh, wait. Conflict.
Could you please elaborate on the concept of referential transparency? It's not clear to me.
What referential transparency is? What's your... Sorry.
The concept of referential transparency.
Okay, so the concept of referential transparency is just the ability to swap out the invocation of a function with the result of the invocation. And that wouldn't in some way alter the behavior of the rest of the system. So it's just an expression to say that there's not one code inside the function that alters the behavior of your system as a whole, if that makes sense.
It makes sense. Thank you.
Okay, so I had a question. When the... Here?
Yeah.
That's right. Obviously, when you have this state, like in a one global object, it becomes kind of like very big and complex. So what's your solution to structure the state? Do you like structure it somehow as the element tree, or how are you doing that one?
It won't necessarily become complex. It will be big, not necessarily complex, but you could also split up your application to sub-modules and sub-parts of your system which have, in turn, their global objects, if you will. So you can have a tree of global objects as well if your system is large enough. It depends on how you use it. So you can split up the different components as modules and have subparts of your page, one global object, and perhaps a global object on the top that stores the global objects. So yeah, tree of trees.
Okay, thanks.
Okay, one more question. The one in the first row.
What are strategies for sharing global immutable state between a client and a server? Are there strategies for sharing global immutable state between the client and the server? Does it make sense to do that?
There are some initiatives, some code bases that try to patch or do like scuttlebutt things with the structure on the server side and on the client side. So yeah, there are a few links on it on the GitHub page.
You mentioned Omniscient, which is really modern and fun technology to me. You are maybe aware of presentation from Martin Kleppmann about event streams, that in your system you have log of immutable facts. If you know that presentation, have you tried build front-end system like that there is only this event stream?
Yeah, so I've used reactive extensions or Bacon as well, but I usually use it to abstract like time-dependent or data-dependent asynchronous achievements. So you can use still reactive extensions and event streams to do. And
it will nicely play with Omniscient.
Yeah, as long as you update the global state and invoke the system, when you can have any integration point you want, right?
Okay, thanks.
Yeah.
So it seems like everyone wants to pick your brain, but we have another talk. So thank you, Mikael. That was amazing.
Thank you.
Thanks for all the questions. So if you want more questions, just catch Mikael afterwards.